So first, I would like to congratulate Professor Roger Wiegand and Professor Sylvia Wiegand on the occasion of the 150th birthday. I had a chance to meet you in 2008 in Barcelona. There was a conference there. And I asked Professor Sylvia Wiegand several questions, and you encouraged me very much. After that, I can write some paper on this, on various present theorems. So, and I expect very much that the book with Professor Heiser and Professor Rothau will appear officially soon. Okay, so I'd like to thank the organizer, especially Victor and Thiago, to invite me to Brazil. This is my second time. My first time was last year during the ICM. But this is the first time I have a direct contact with colleagues in Brazil, mathematically. Yeah. So, and I also have a chance to meet many people. I just hear the name, but I never seen you directly. So it's a very good opportunity for me. Thank you very much. So today I would like to talk about positive subscheme of almost maximal degree. This is my joint work with Professor Sejong Kwak from Korea Advanced Institute of Science and Technology. So people talk about the variety of minimal degree, and today we will talk about maximal degree. So what does that mean? So I start with degree bound for subschemes. So net I fix some notation. S0 will be a polynomial ring over an infinite field in n plus e plus 1 variable. And here I consider the graded K algebra is quotient of S0 by I. And we know that we can choose some linear form such that this algebra is a natural normalization of R. And if we consider R as an S modules, and we choose a homogeneous generator, and we choose a minimal set, say B1, Bs, then the reduction number of R with respect to S is defined as a maximal degree of the generator. So, and the reduction number of the algebra is defined to be the minimal of the reduction number of R with respect to any natural normalizations. So to define the reduction number, we can use a minimal reduction. And here the minimal reduction is just a minimal reduction of the maximal homogeneous ideal. So to get the degree up above, now I consider a non-degenerate positive subscheme in P n plus E of codimension E. And I denote by Ix the defining ideal and Rx the homogeneous coordinate rings. And we can assume that the algebra generated by Xe to Xn plus E to be the neutral normalization of R. Then the algebra R, I'm sorry, here should be Rx. Rx is generated over the polynomial ring S by monomials in X0 to Xe minus 1 of degree at most R, just by definition of the reduction number. So because of this, we can, we can get it upper bound for the degree. So if we count on the minimal monomials in X0 to Xe minus 1 of degree at most R, we have R plus E to E. So the degree of X is less than or equal to this number. So this is a starting inequality for us in our work. And so there naturally several bounds for the degree. So here I would like to mention the bound by the Castan-Nouveau manifold regularity. So it's similar to our bound. but here we replace the reduction number by the regularity. And later I will compare our bound with this bound. And another one is the lower bound by the codimension plus 1. And I guess called the minimal variety if the degree equal to this minimum. So codimension plus 1. And this the variety was studied by many people from the 19th century. And we can say it's the final step was completed by Eisenberg and Harris' work. And we say that X is almost minimal if the degree equal to minimum plus 1. And this the variety was studied by Vogel, Stuttgart, Hua, Pressman, Sensei, and many other people. So come back to our bound. We also consider the case the upper bound is achieved and almost achieved. So this our arm is compute the Betti diagram of the variety when the degree equal to the upper bound or equal to the upper bound minus 1. Now I go back to the reduction number. First, I recall the Betti table. So let's R be a question of S0. S0 is a polynomial ring in x0 to xn plus e as before. Then it has a minimal free resolution like this. And the Betti table is, has this shape. And this position is only 1, 0, 0, and other Betti numbers is 1. And the size of this Betti table is positive dimensions and the Carsten-Wolff rarity. So it's the size of the table. We say that the algebra satisfies the NDP property. So if we look at the Betti table, it means that this corner is 0. So here is D and here is P. So DP mean NDP property means that this rectangle is 0. So this notion was given by Eisenberg-Goto and Eisenberg-Green, Holek, and Popescu. So if we look at this one, then we can see that if D is bigger than the regularity, then R is all the way NDP. Yeah. And another invariant related to the reaction number is A invariant. So if we denote by SR plus R, the local chronology, then we define the AI to be the supremum of the non-vanishing degree of this graded modules. And the regularity of R is a maximum of AIR plus I for on I. Then there's some relation between the A invariant reduction number and regularity. It was given by Cuong in 1986. So the reduction number is between the regularity and the A invariant plus N. So I'm sorry, N here is the dimension of R. The number N here is the dimension of R. Yeah. And equality occur if R is coherent. I mean both equalities. And there's another comparison between the reduction number and I want to say that by this one, if we look back the upper bound for the degree, then this upper bound and this is the second upper bound, then our upper bound is a little bit better. There's also another comparison between reaction number and the other invariant, namely if R satisfies the NDE property. So here E is codimension. Then we can compare the reaction number and the D minus 1. D is this index. And D is the most smallest one, so that R satisfies the NDE property. and the number is less than or equal to the regularity. And there are examples such that the reduction number can be very small to compare to the regularity. This is Ulrich's example. So in the example, we have a polynomial in 4 variables, and I is generated by this one. And t is any number bigger or equal to 2. In this case, the normalization is k x2, x3. And this is a Betty table. So by this, we can see that the regularity is t, but the reduction number is 1. So once the reduction number is fixed, the regularity can as big as possible, as we want. So now I go to the maximum case. So the maximum case, so I just recall the notations here. So we have the positive subscheme, non-degenerate, in Pn plus E. And we fix Noether normalization. So here we suppose that it is generated by xe to n plus E. So here's our upper bound. We will consider the case that the degree equal to this upper bound in this part. So here I recall that X is called an arithmetically coherent subscheme if the homogeneous coordinate ring is coherent. Then this is a theorem about the Betty table of maximal variety. So the subscheme has maximal degree if and only if it is arithmetically coherent with an R linear minimal free resolutions. So linear resolution means that in the Betty table we have only one line here. So it's so in this case we can compute precisely the value of the Betty number in terms of the codimension and reduction number. This theorem was proved first by Han and Cuong in 2017. And in their paper, they assume that X satisfies the NR plus 1E property, and the characteristic of the field is 0. And here we just do not assume anything. Then somehow this theorem is a little bit stronger, and I also want to mention that in their work the proof is quite long because they come from geometry, and for us from algebra to show that if the degree is maximal implies ACM is not very difficult because it's somehow the leg inequalities. We have the equality between the multiplicity and the length, and then almost immediately implies that the variety is ACM. But in their work they give another proof, and it's quite long, and they use characteristic 0 assumptions. Yeah. So now I want to give some application of this theorem. So I want to recall that for projective variety, the degree is always bigger or equal to the codimension plus 1, and we call it minimal variety if the equality occurs. Then we have the following consequence of our previous theorem. For non-degenerate projective variety, the following are equivalent. The reduction number equal to 1, the regularity equal to 2, or the variety is minimal. So B and C are equivalent group known by people, but here we add one more equivalent conditions. reduction number equal to 1. Because if the reduction number equal to 1, then then if we look at this, I'm sorry, if we look at this inequality, if r equal to 1, then the degree is less than or equal to e plus 1. But we know that the degree is bigger or equal to e plus 1, so it must be equal to e plus 1 in this case. Another application is to, we also want to study variety with reduction number 2. But in this case, it's very hard, so we have to assume that the variety is ACM, arithmetically coherent. And with this assumption, we can describe the Betti table of the variety. Here we can have only the relation between two Betti numbers. We cannot have a precise formula for each Betti table because it does not exist. If we expect something depend only on the codimensions. So here is an example of a sucker-type variety. So if we take the D'Ampezzo variety of dimension n, then the degree is e plus 2, and the reduction is 2. And this is the Betti table. This was given, I think, 20 years ago by Wa. Now we go to the almost maximum case. So for the maximum case, the variety is ACM. But for almost maximum case, we don't have it anymore. So it's much harder to study this case. So we have to separate into two cases. One is maximal, one is ACM, and one is non-ACM. For the ACM, it's not difficult. So we say that I is almost maximal degree, has almost maximal degree if the degree equal to upper bound minus 1. And in this case, we have the following characterizations. Suppose that I is ACM, arithmetically coherent class, then it has an almost maximal degree even only if the ideal, the defined ideal has this property. So the truncated at the reduction number has linear minimum resolutions. This is so in our work, usually we, if we want to study variety, we first describe the ideal or the initial ideal, and then we go to the Betti table. You will see later. So this is an example of second variety. This example is taken from Hasson's books. It's a curve degree 5 and zenith 2. And in a paper in 2002, Naito so that this curve is ACM, and he computes the regularity of this one. So the regularity is the curve is 3, and the reduction number is 2. And in this case, because we have the degree 5, so she has almost maximal degree, and the Betti table is this one, like this. Other example, such varieties contain the Casimir-Monfort surface, Casimir-Trifle, and so on. So I don't go further in this example. Now I go to the Betti table of almost maximal variety, which is ACM. So let X be a non-degenerate subscheme, and we assume that it's arithmetically coherent class. Then the subscheme has almost maximal degree even only if the Betti table has its shape. So the second line, we have only one here, and the other Betti number are computed by the formula. So in this case, we can compute it precisely, the Betti number. Now we go to the almost maximal case, and non-ACM, non-arithmetically coherent class. In this case, we have to assume that we have to work on variety instead of subscheme. So this the key theorem is the following: if X is a non-degenerate positive variety of almost maximal degree, then the depth of the homogeneous coordinate ring is at least the dimension of the variety. So there are only two cases: one, the dimension of the variety, or the dimension plus 1. If the dimension plus 1, then it's ACM. So we consider already. And the remaining case is is non-ACM, so the depth equal to the dimension of the variety. The proof of this theorem is rather long. The main the key idea is because we consider variety, then we use to prove this theorem we use the Grobner basis techniques. So because the variety is because X is variety, then if we take a reduced Grobner basis, then it must consist of irreducible polynomials. It's very important in our proof. Then we can, from this, and because the degree is almost maximal, then we can describe the initial ideal. We will see later. And from this, we can use one we can describe explicitly the initial ideal. Then we have the comparison between the positive dimension of R and of the initial ideal. Which is this one. This is a concatenation principle of Mark Green and other people also. Then using this, because we can using this we can imply the this in conclusions. And I have a couple of remarks. First remark is the first remark is this theorem is not true if we if variety are replaced by subschemes. We can imagine because the degree depend on the Higgs associated primes. So if we put some other associated prime, then we think have the degree, but we don't have the condition on the depth. So the second remark I already said, that if X is not ACM, then the depth must be equal to the dimension of R. And here is a description of the initial ideal. So we keep the assumption in the previous theorems. And here we assume that this algebra is a Noether normalization. So the algebra is read by xe to xn plus e. And we fix the reverse lexicographic order, the degree reverse lexicographic order. Then X is almost maximal degree and not ACM. If and only if the initial ideal is generated by monomial in x0 to xe minus 1 of degree r plus 1 plus 1 monomial ZV, where Z is a monomial in x0 xe plus minus 1, and V is a monomial in xe to xn plus e. Because of description, since we can, it's quite explicit, then we are able to compute the Betti number. And this is, if we consider this algebra as a module over the Noether normalization, then we compute precisely the Betti number. This is the formula. And we use this to give the graded Betti table for the variety. So now X is a non-degenerate variety, and we assume that it's almost maximal degree and not ACM. Then the Betti table are described in several cases. So we have the regularity of Rx is bigger or equal to the reduction number. So this is the reduction number of Rx. So we have to separate into several cases. So for the first case to consider is when the regularity equal to R. In this case, the Betti table is like this. There's only one line here. And we can compute all the Betti number explicitly. The second case is when the regularity equal to R plus 1. And in this case, we have the Betti table has this shape. So there are two lines at R and R plus 1. And in this case, we cannot compute precisely the Betti number. We can have only the relation of this case. I will come back to this later. And the last case is when the reality bigger than the real number plus 1. In this case, we can compute the Betti table precisely. So it has this shape, the two lines at the real number and at the reality, and this is the formula for the Betti number. Yeah. So the question is whether they exist. Do we have an example of this kind of variety? So I'd like to give some example. So the first example is shape A. So shape A means that the reality equal to the real number. So in this case, we also take an example from Hassun's book. It's a curve in P3, degree phi and genus 1. So this is the real number equal to 2, and this is not ACM, the reality equal to 3. So this is also an example of variety such that the reality equal to the real number, but I mean real number plus 1, but it's not ACM. So this curve is almost maximal degree and not ACM, and the Betti table is like this. It's just only one line here. So the second example is a curve sub B, such that the Betti table has sub B. So sub B means that the reality equal to the real number plus 1. Is this so this is a rational curve defined by this map. So this is a smooth curve of degree 5 and genus 0, and this is a Betti table. We can compute it like this. And this is exactly the example for sub B. And for C, we have the example. This example is very complicated. We take the rational curve in P3 and of genus 2 defined by this map, and this is a Betti table. This is not ACM, and real number is 2, and the degree is this one. So for this example, I have to take Macquarie 2. Without Macquarie 2, I think I cannot find this example. So because theoretically we can describe the Betti table, and so we can use Macquarie 2 to search. So after maybe a half an hour, we found the example, and we're very happy.
I can also do it in Macaulay 1. Still running, and I still use it.
Okay, so so here we have a three shape of the Betti table. The first and the third scale we can compute the Betti number precisely, but the middle case we cannot compute the Betti number precisely. Now, in the last part of my talk, I want to discuss about this phenomenon. So it's related to the what we call common one linearities. Okay, so here I recall the shape B. So in this case, the reality equal to the real number plus 1. And the Betti table has this shape, and here we can have only relation between Betti number. And the question is whether we can compute this Betti number precisely. So this question related to the ideal structure of the defining ideal. So what? So here I want to recall the definition of component one linear solutions. So let I be a homogeneous ideal in this polynomial rings, and we denote by ID the ideal generated by only degree D homogeneous polynomial in the ideal. And we say that I has a component y linear resolution if ID has a linear minimal free resolution for only for any D. So this definition was given by Herzog and Hebe, and later it's find many applications in commutative algebra, and also in combinatoric commutative algebra. So here's some remark about this this type ideal component y linear. So if I is linear, then it's a component y linear. And as a third example of this notions, has shown in here so that if a standardized ideal is component Y linear, if and only if the Alexander dual is sequentially coherent. So it have a very close relation to the coherent property and sequentially coherent property. And there are many examples and many work on monomial ideal which is component Y linear, but not so many examples of component Y linear prime ideals of variety. So here I would like to mention two of them. One is by Francisco Miglio and Nagel. They characterize tetrahedron curve with component Y linear resolutions. Another one is by Nagel. It shows that almost on curve with maximum Hudson routes module are component Y linear in characteristic 0. So this part of our work was motivated by a question of Satoshi Murai from Waseda University in Japan. He asked us whether on positive variety of almost maximal degree are component Y linear. This question is very reasonable because if we look back the ACM case, so in theorem 5, if a variety has a maximal degree, then it is linear. In theorem 9, if x is not maximal but x is almost maximal, and ACM, if and only if the ideal have satisfied this property, so the degree R is generated by one polynomial, and for the truncated ideal R has linear resolution. So in this case, it's also component Y linear. Now we have our main theorem for this part for the component Y property. So let X be a positive variety of codimension E and direction number R, and we assume that X has almost maximal degree. So the maximal degree we have is linear. So now we are interested in the almost maximal degree. I'm sorry, here we should say that X is non-ACM, non-arithmetically coherent.
So you don't know whether it's linear. You said it's linear in the ACM case. Linear resolution in the ACM case.
Yeah, if so it's maximal, then it's linear. But if it's almost maximal and ACM, then it is component Y linear, but not linear. And now we go to the almost the remaining case. It means that almost maximal, but not ACM. So in this case, we have the following theorem. So the variety has component Y linear resolution if and only if the first case is regularity equal to R. This case we see already when we see the Betti table. There's only one line, so it's linear. In this case, it's linear. The third case is when the regularity equal or equal to R plus 1. In this case, we can compute the Betti number precisely, and in this case, the variety is component Y linear. And the middle case is when the regularity equal to the reduction number plus 1. In this case, we had to separate into several cases. So if the Betti number beta 1 R plus 1 R is 1, then X is component Y linear. And the second part of the theorem saying that the variety is not component Y linear if and only if in the middle case, but the Betti number equal to 0. So in this case, there's only two possibilities for the Betti number beta 1 R plus 1, either 1 or 0. So if it's 1, then it's component Y linear, and it's 0, and it's not component Y linear. Yeah. So using that theorem, we can skip the Betti table in the case of component Y linear. So so we assume that X is almost maximal degree, the regularity equal to R plus 1, and the Betti number R 1 R plus 1 equal to 1. then the Betty table has a shape with precise formula for the Betty number. It's like this one. So if we go back to this theorem, so in the case of component Y linear, we can compute precisely the Betty table, and the remaining case now is non-component Y linear. So here we give example to say that this corollary is has some meaning because there are some variety satisfy these conditions. So this is an example. So in this example, we have a current P3 and it's almost maximum degree non-ACM and the regularity equal to R plus 1 and the Betty. I'm sorry. The example satisfies this one we have already before. It's a shape B I mentioned before. And this example saying that the remaining case is also acids. So in this case, we have a almost maximal variety. The regularity equal to reduction number plus 1, and the Betty number equal to 0. So in this case, it's not component Y linear. It's not component Y linear. Yeah. So this example saying that kind of variety also exists, and the question is how to classify their Betty number at Betty table. We don't have at the moment result about this. So this is a summarize of this one. So this is much more sub-scheme. It must be ACM linear, and we can compute the Betty number. Almost much more and ACM we can compute. It's component Y linear, and we can compute the Betty table. Almost maximal non-ACM, and the gravity equal to R plus 1. We also can compute the implicit Betty number, and it's also component Y linear. Now, the remaining case regularity equal to R plus 1. So in this case, we separate into two subcases. So this, if the Betty number equal to 1, then it's component Y linear, and we can compute the implicit Betty table. And this case, it's not linear, component Y linear, and we just have the Betty table with relation between two Betty number, but we don't have a precise formula for this one. And I don't think we can have a precise formula. Maybe it's going separate into many subclasses. Yeah. Okay, so thank you very much for that. Questions.
Come clear from what you said? Which one is the degree where it's not linear? When it's not component-wise linear?
Yes.
In what degree it fails? Of the idea? In what standard degree? Does it fall immediately, or you have to compute?
Yeah, it's very good question. I have a thing about it. Yeah, it's a good question for me. Yeah, I haven't think about it. I have no information about it. The degree is not linear. Maybe I had to compute. I mean, here we have an example, and I can compute it later. Yeah, I have to do Macaulay 2 and so on to compute it. So I cannot say it. Okay.
Yeah. Two general questions. General. That 1986 result by Coung that you showed in the previous slide, could you put that, please? Yeah, Coung.
This one.
Yeah, it's a quite old result. And this AI variants are defined in terms of local cohomology. So it would be natural to ask whether this result has an analog for generalized Cohen-Macaulay modules. Oh, sorry, rings. Generalized. Do you have any characterization of generalized Cohen-Macaulay rings? Meaning that the local cohomology below the dimension has finite length.
I don't know any result of that kind. Yeah.
Characterization similar to this result.
This does say that because the regularity is defined in terms of the A invariant like this one. So if the ring is coherent, so there's only one local chromacy.
Yeah.
It is this A n plus n, so they only equal to each other. It's,
This
yeah,
is, yeah.
yeah. So
Second time.
The equality will occur even if F is at least D minus 1. If D is the dimension.
Okay.
Which one? The
On the left.
uh-huh.
And theorem 5, your result with the collaborators. Theorem 5 is
Theorem 5. This one, yeah.
it's a beautiful theorem. Just wonder whether you have some version for modules, I mean for locally free sheaves, vector bundles, because you have the degree, you have the concept of arithmetic from Macaulay, you have linear concept of linear minimum free resolution for modules which are locally free on the functional spectrum. I'm asking this because this could be of interest
It
to
should be,
approach the theory of Ulrich bundles.
yeah.
Okay, because Ulrich bundle deals with in terms of modules, it's a maximal Macaulay module,
Yeah.
which is maximally generated.
Yeah.
It's generated by the multiplicity of the ring times, suppose that the ring is a domain, which is the case, times the multiplicity of times the rank, generic rank of the module. Okay, so in case equality occurs, we have a Ulrich module. So there's a notion of Ulrich bundle as well.
Yeah.
And then Eisenbach and Schreier has a famous question regarding the existence of Ulrich bundles on a given variety. So since you have here a criterion for, a formula for the degree of x, as well as a Cohen-Macaulay criterion for x, if you get a result like this for bundles, it would be very useful, for this purpose.
Yeah.
For Ulrich bundles.
Yeah, I mean, we didn't think about the modern version of this one, but yeah, I think it's possible. Yeah. Okay. Yes.
So, about questions, thank you very much.